Hello everyone, welcome to the 11th session of Electromagnetic Theory and Interference course. In this session, let us understand how to find the electric field due to continuous charge distributions. So far we have discussed the electric field due to point charge, right? Okay, now there is a possibility of having a continuous charge distribution like line charge, okay, which is a line charge density, which is represented by rho L here. The unit is coulomb per meter, whereas there is a surface charge over the surface. The charges are distributed. This density is represented by rho S. Unit is coulomb per meter square, and there can be a charge over the volume. That density is represented by rho V. Volume charge density, coulomb per meter cube. Okay, and this rho is different from the row that we used in radial distances cylindrical coordinates. Okay, so the charge element dq and the total charge q we can find for these distributions via this relation. We already know differential charge element is equal to rho L into dl. Okay, so same I can write for the surface charge density and volume charge density, and we have to take the surface charge differential surface area from volume charge differential volume. From this I can find the total charge for all these charge distributions. That is Q is equal to if I want to find the Q, I have to take integral on both sides. That will remove my differentiation on the left hand side. So Q I will get as integral over the line rho L dl, over integral over S rho S dS, integral over V rho V d. Okay. So in our course we are going to concentrate on the line charge distribution. Okay. And before moving further for the line charge distribution, so let us understand how to get the electric field intensity due to various charge distribution. So we already know the relation that E equal to F divided by Q from Coulomb's law. From that, one charge will be present, that is due to the point charge. I can find Q divided by 4 pi epsilon naught R square into AR cap by substituting the Q values from the previous expressions for the different charge distribution, and these term will be same. So for epsilon naught R square will be there, but for Q it is rho L dl, okay, and for here it is rho S ds, and here it is for rho V d. So the it differs line integral, surface integral, and volume integral. Now let us understand um, how to find the electric field intensity due to line charge distribution. Here my charges are distributed along the z axis from the point A to B. Okay, and it is having the line charge density rho m. Okay. We are going to consider a differential element dl where my different charge element dq is present. So the dl is going to be dz here. So we already know the relation dq is equal to rho L dl. Here I am going to substitute since it is around z axis I am going to change dl to dz. Okay. So the total charge how will I find? Just integrate from za to zb the points where my charges are distributed and rho L into dz. Okay. At this relation we are going to substitute in this generalization of electric field intensity. Okay, before doing that, let us understand this is the point where my electric field intensity is to be computed. So if I can write as a vector form, okay, there are two components. One is along this row component. So I have taken row, B row, okay, and this is along the Z component, D, Z. So the total electric field will be the resultant vector of these two vectors, D, Z. And how this alpha comes, let us understand. So we are considering the differential element dl, right? The point from there to the point where I want to find the electric field, that radial distances are. Okay, and the angle that this straight line, horizontal line makes with this particular radial distance is alpha. So this alpha turns out to be same in this case, right? Both both are opposite. And here if I have considered a point A, right, and the radial distance of the point A from this horizontal axis is alpha 1, and similarly radial distance of point B from the horizontal axis is alpha 2. Okay, and here this T is taken as 0, position as 0, Z, but here I am considering Z dash. So usually we will take from this thing we can understand. And so the point at which I need to find a field is taken as x, y, z. The point at which the source is that. This is the source position, right? It is called x dash, y dash, and z dash. So now let us change our dl not to dz, now dz dash. Okay, and in this above expression, we are going to substitute few things. For the Q, we will write rho L dl, that dl will be changed to dz, right? Okay, and for the unit vector, we need to find separately. And this small r square is now going to be changed to capital R square. We are going to find all these values and we are going to substitute here. So first find the capital R. It is nothing but this is at a point x, y, z. This is at a point 0, 0, z dash. So how can I write it as a vector? X minus 0 is x, a x cap, plus y minus 0 is y, a y cap, plus z minus z dash into a z cap. So this x plus y, I can take it as rho. Okay, so R equal to, this is rho A rho. If I take a right angle triangle, you can see rho A rho plus Z minus Z dash into A Z cap. So how will I find the square, R square value for this relation? It is magnitude square. So magnitude, if I take, it should be root, but the squaring I will get. So directly take considering this right angle triangle, if I write rho square plus z minus z dash the whole square. Since this rho square is nothing but x square plus y square, right? And how will I write the unit vector? It is nothing. So this term is the AR divided by R square. That only is written here. So this will be a vector divided by its magnitude. Already one magnitude is there. So magnitude 2. So what will be the vector that we have found is here? Then the magnitude part I have to uh, find the magnitude and take the cube. Magnitude taking means it is taking square root, that is 1 by root 2 I can write, power 1 by 2. The whole cube will be coming as 3 by 2. So everything what and all we got, and we applied this Q and Royal relation also, we have come up to this expression. For Q, Royal divided by 4 by Royal DL will come. I told it as D is a dash. Okay, and 4 by Royal also constant, 4 by epsilon are constant here. I have substituted AR divided by uh, R square. That value only I have substituted. Okay. Now our task is to find what is rho z minus z dash, right? And we are going to change the integral from z axis to the angle alpha, okay, d alpha. Now let us see how to do that. So for doing that, consider this highlighted red color portion of my right angle triangle, and I am going to write sine alpha and cos alpha. We already know sine is nothing but opposite by hypotenuse. Opposite is what? Z minus z dash. Hypotenuse is capital R. So z minus z dash is R sine alpha. Similarly, cos alpha is adjacent by hypotenuse. Adjacent to this angle is rho by R. From this I can find the rho value. From the rho I can write what is R. So R is nothing but rho by cos alpha. 1 by cos alpha we already know it is secant alpha, right? Now R equal to rho secant alpha. And in this z minus z dash, this expression I am going to substitute the value of r, that is rho secant alpha, and I am going to again write it as 1 by cos alpha. What is this sine by cos? It is going to be tan. So why we are doing this? We are going to find what is z dash, because in our original expression we need dz dash, right? So z dash we should know. Z minus, so if I take this side, we go tan alpha. So differentiation of this dz, we are going to change the integral to d alpha I tau. With respect to alpha, what will come? Here there is no alpha term, so 0 minus rho will be a constant. Integral differentiation of tan is minus secant square alpha. So dz dash is nothing but minus rho secant square alpha. Now we are going to substitute everything here, that is rho L by 4 pi epsilon naught is same, and this integral now changed to alpha 1 to alpha 2. Okay, here the lower limits are not visible, it is alpha 1. Here for rho it is r cos alpha a rho cap plus z minus z dash we have found as r sin alpha into a z cap. For d z dash we have just now found this relation minus rho secant square alpha d alpha, and here we are not using this term, we are just directly taking the entire term, that is r square whole power 3 by 2. So this 2 and 2 get cancelled and we get a r cube. So that r value I am substituting. R is nothing but rho secant alpha. So r cube is rho cube secant cube alpha. Now I am taking one more thing as out constant. That is r is same in this vector equation. So for r also I am substituting rho secant alpha. So this rho secant alpha that will be at numerator. So cancelling the common terms. So here also we have. What is left now? Only one row will be left because numerator rho square is there, secant cube is there. Okay, that row is a constant, so I have taken it out and I have written the remaining things along with d alpha. Now we are just going to substitute the limits. Find the integral of cos alpha with respect to d alpha, it is sin alpha. So applying the upper limit, sin this already negative sign is there, I have just taken inside sin alpha 2 minus sin alpha 1 into a rho cap. For integral of sin alpha, what is the result? It is minus cos alpha. Already one negative sign is common out, right? That negative and integration of sin alpha, that is minus cos alpha, that negative turns out to be positive and we get cos alpha. So applying the upper limit and lower limit, cos alpha 2 minus cos alpha 1 into a is the cap. This is my electric field intensity due to finite line charge distribution. Now we are going to see one more special case where I am going to consider infinite line charge distribution. Already we have found for finite charge from A to B, if the charge is distributed, okay, line charge is distributed, what is the electric field intensity? Now let us take infinite line charge. That means my now point A will be 0, 0 minus infinity, whereas my point B will be located as 0, 0 plus infinity, right? What happens to my alpha 1 and alpha 2? This alpha 1 turns out to be plus pi by 2, alpha 2 will turn out to be minus pi by 2. So we are going to substitute everything in this above expression. Okay, we already know that sine of minus theta is equal to minus sine theta, and we know sine 90 degrees 1, cos 90 is 0. Okay, so substituting these things, alpha 2 is now, what is the limit? It is now minus pi by 2, right? So already a negative sign is there, sine of minus pi by 2 minus sine of plus pi by 2 into a rho cap. Since cos of 90 is 0, cos of minus 90 is also 0, I just neglected this term and I have written 0 a is a cap. This might be 0, right? Now we have to substitute the value of sine of minus 90, which is minus 1, minus sine of plus 90 is 1. So altogether we get a plus 2 here. The 2 and 2 get cancelled. The final result is rho L divided by 2 pi epsilon naught rho a rho cap. The Z component for transition. I hope you understood how we arrive the electric field intensity due to continuous line charge distribution and infinite line charge distribution. Happy learning. We will see you in the next session. Thank you.